Welcome everyone to this joint CRS Nordic Local Chapter and NordicPOP webinar. And today we have the pleasure of welcoming Professor Thomas Rades from University of Copenhagen, Department of Pharmacy. And he's going to share with us his extensive knowledge on amorphous drug research and development.
Question of amorphous stability, and we'll spend some time on that. And then towards the end, I want to just start highlighting a few things that we are currently working on. And that is the question of polyamorphism, or maybe even pseudo-polyamorphism. And then the effect of a second component on amorphous drugs. And here we do not mean coamorphous systems or amorphous solid dispersions, but a small amount of another component. What does it do to the amorphous drug? So I have to say thanks to a lot of people. When I put these slides together, I realized that this is a very many co-workers, many former PhD students that now have finished. I don't want to read out the whole list here, but you see a lot of names here that maybe are familiar to you. People are working now in industry or in academia or indeed in the office next to me. So there's a few people I like to thank here, because basically it's their work that I am presenting here. I also want to point out before I start that we have a lot of other activities in the group on amorphous systems, not only the pure drug. For instance, we are looking currently at the influence of polymer addition to coamorphous systems, influence of water to coamorphous systems, phase separation, eutectics and co-crystals as precursors for coamorphous systems. A lot of activities in this area with PhD students and postdocs, and this is always done in collaboration with Holger Grogans from our solid state analytics group. In fact, my head of the group. We have other areas where amorphous materials pop up here, and this is, for example, looking at maybe unusual coformers, for instance, lecithin systems as drug coamorphous systems with lecithin, and then also amorphous systems in advanced lipid-based drug delivery systems. A very exciting area, and we also have a few PhD students, postdocs there, and this work is always done in collaboration with Annette Müllertz. Then we also have activities around the formulation side, or maybe going into sustainable formulation of amorphous systems. So we have some kind of chemical activations here, several people involved in this. And then a very exciting postdoc that we have in the group now from Japan, who is looking at high shear granulation for amorphization. And then we have a lot of collaborations with other groups in Hamburg, Oslo, Helsinki, Obo, on various amorphous systems. So I'm not saying this to say we're doing so much. I'm saying this because I think that this amorphous field and research in amorphous systems is actually sort of a stronghold in the Nordic area of the world, and also a lot of NordicPOP members are part of these activities, and much of this work is done collaboratively. But now I'm talking only about drugs. And initially we talk about the amorphization path and amorphization propensity of drugs. So many of you will know this, but it is going like a red thread through the presentation. So just by way of reminder is that we basically can differentiate two ways how we can convert a crystalline form into an amorphous form. One is known as the thermodynamic path, the other one's known as the kinetic path. In the thermodynamic path, we are using either heat or a solvent to initially create a high energy yet thermodynamically stable system. So either the melt, which is the stable form at the high temperature, or a solution, which is a stable form in solution for the drug. And then we are either cooling the melt very rapidly, or we are removing the solvent, also preferably very rapidly, and we are ending up in an amorphous form. So it's called the thermodynamic path because intermediately we go through a thermodynamically stable system here. So either cooling the melt or getting rid of the solution, and then technically this is realized in systems like melt quenching, or also melt extrusion on the one hand, and spray drying, for example, on the other hand. There's, however, another way we can go, and that is the kinetic path. Here we are introducing more and more disorder into the crystalline form. And eventually we have so many defects in the system that the crystal doesn't hold together anymore. And we are again ending up in an amorphous solid form. In this path, we always are in non-stable situations. Therefore, it is called the kinetic path. And it's technically realized, for example, in milling, then often called mechanical activation. So this is a path that is perhaps getting more interesting, also with a view on sustainable formulation of amorphous systems. So thermodynamic path, kinetic path. So then we can make drugs amorphous following these two paths. And this is some work that Lasse Blauberg has done. And we looked at amorphization either by cooling a melt or by milling a material. And then you see here the X-ray diffractograms, for example, of silicon, that if we are making a melt and then from the melt, we are cooling at various cooling rates, then you can see that at some cooling rates, for instance, 15 centigrade or Kelvin per minute, we get a recrystallization of the drug. Whereas if we take a faster cooling rate, 20, 25, 50, we are retaining an amorphous form. And we can see this in this typical halo of the amorphous form in the X-ray diffractogram. In the milling, it works like this. We're milling the sample, and then we are taking the sample out after some times, and we're determining if there is still residual crystallinity, and we can determine something like a minimum milling time for the drug. So it's a very simple DSC or milling-based way that we can determine the propensity of a drug to turn amorphous via the thermodynamic path or via the kinetic path. And if we do this via the thermodynamic path, we can also use so-called TTT diagrams, which are time temperature transformation diagrams. We got this out of the metallurgy, where this is used quite a lot in alloy, research on alloys and so forth. But the same can be done for drugs. So we make the drug amorphous, and then we store it at different temperatures in the DSC, for example, and we just wait until it crystallizes. Then we see a crystallization event happening, and we record the time that happens. And if we do this at various storage temperatures, we're going to form this so-called nose of the system, or the zone of nucleation and crystal growth. If you now draw a tangent from the melting point of the material via the tip of the nose, you get the critical cooling rate, meaning that any cooling rate faster than this will lead to an amorphous form, and any cooling rate slower than this from the melt will lead to crystallization. So if it's slower, you would follow this path, for example, and boom, you touch the nose, the system will crystallize. If you cool faster, you go somewhere through here, and then you will not get crystallization. So we can very simply determine the critical cooling rate of a given material. And if we do that, and we also look at the minimum milling time that is necessary to convert this drug into an amorphous form, then we see that drugs seem to be falling almost naturally into several categories. So these are just some examples. We have many more, but we always find one category where even the highest cooling rate that is possible, we call it the ballistic cooling, or very long milling times, will not lead to a complete amorphization of the material. We have another group of drugs where the critical cooling rate is around 10 to 20. And we have another group where it is around 1. It's almost logarithmic. You can say 1, 10, 1,000, if you like. So that means that drugs can be fairly easily grouped in according to their propensity to be converted into an amorphous form. And this holds true for the thermodynamic path as well as the kinetic path. So here are some more examples of these drugs, class 1, 2, 3. And it seems we have, of course, not looked at 1 million drugs, but anybody who wants to do this, please let us know, because we want to see if these classes that are almost logarithmic in terms of their critical cooling rate hold true for drugs, or if there are exceptions. We haven't seen any. So once we know that we can convert a drug into an amorphous form, we should then ask ourselves, is it even worthwhile doing? And for that, we need a method to determine its propensity to supersaturate. And we have done this also some time ago with Annette, of course, and then Cecilia and Jakob and Henrik. And what we try to do here is having some sort of a standardized system in order to measure the ability of a drug to supersaturate and also to maintain supersaturation. I don't want to go in great details. This is all published, but basically what we do is we initially add the drug in DMSO dissolved to our solvent, usually Fessiv or something like that, and we add more and more and more and more, and then we get a beautiful standard curve here, and eventually we're going to see a deviation from linearity, and that's due to precipitation. Then we have overdone it. We have added too much drug, and the drug has immediately precipitated. Then we go a little bit back, and we choose certain concentrations that are around about 100%, 87, 75, and 50 of the maximum drug concentration that we can add before we get immediate precipitation. And then we are getting curves like you can see here below, that we are getting some time that the drug stays in solution and then it crashes out. And if we do this at these 4 concentrations that are now, so to speak, normalized for all drugs against their maximum ability to contain drug, then we get curves like this, where we see that with increasing concentration of drug that we add, that then the induction time gets shorter, and then crystallization or precipitation occurs. And if we have a little bit less drug, it can stay in solution longer, even less, even longer. And at some point, even over the course of the experiment, it won't precipitate at all. And the red line here is always the equilibrium solubility of the crystalline form of the drug in the medium that we're studying. So when we have these kind of curves, we can apply nucleation theory to it, and eventually we get curves where we can plot the induction time against the degree of supersaturation for these various degrees of supersaturation that we have pre-chosen. And that allows us to compare different drugs. And now we can look at these drugs according to their ability to supersaturate, and also at degrees of supersaturation that will be maintained for very long times. So for these drugs here, not a high degree of supersaturation can be maintained for very long times, but for these drugs here, a higher degree can be maintained for a longer time. So now we have some sort of a tool that we can say, okay, for this particular drug, we would need an increase in the degree of in this solubility by 4-fold or whatever, and then we can estimate how long this drug would be stable in an amorphous form, would stay dissolved in the amorphous form. So that's super handy, because it tells you that if the drug is worth it to be developed into an amorphous form, or if we need to do something, for example, adding a precipitation inhibitor like HPMC or PVP. And then we see that if we do this, our curves, they shift to the right, and we can estimate the effect that an added precipitation enhancer will have on maintaining supersaturation for a given drug. So that's all super fine and dandy, but then of course not always. We ask ourselves the question: is a drug added in DMSO, is that even resembling what happens with an amorphous form, or what happens in vivo? So in vivo, oftentimes supersaturation is induced through a pH shift, but we have shown that the curves we get by DMSO addition of the drug or by pH shift, they are very similar. So it seems that this kind of effect can also be modeled by using a DMSO. Here another example, we get the same sort of behavior for both systems. But of course, usually we are interested in adding an amorphous form of the drug. And then we also could show that the DMSO-based method that I have just described is basically leading to the same maximal degree of supersaturation than if you would add more and more amorphous form of the drug. So if you look at the maximum solubility we reach here by adding increasing amounts of amorphous material, we get the same limit as we get for the determination of the maximal degree of supersaturation that we get from the solvent shift method. Why am I saying this? I'm saying this because these experiments are very easy. And if they are easy, then that's great. But are they also telling us something? That's even better. And they do, because if you remember the glass forming ability classes, the ones that couldn't be made amorphous, we call them class 1. they would also then show a maximal degree of supersaturation of 1, meaning they can't supersaturate, right? Because you can't get them amorphous. How could they supersaturate? And then the class 2, where we needed like intermediate cooling rates or medium milling times, we are usually getting a maximum degree of supersaturation after 24 hours that is comparable to what you could expect from a high energy polymorphic crystalline form. So in the order of 1.5 to 2. Whereas if your drug is very easily amorphizable, it will also lead to a high maximal degree of supersaturation. So if you can make a drug amorphous easily, maybe with a low cooling rate or with short milling times, you have a reasonable expectation that the maximal degree of supersaturation you can achieve with that drug will also be high. So basically by 1 or 2 experiments, you can look at the usefulness of a drug to be converted into an amorphous form. So that's super duper. But then what about the amorphous stability? If we want to use an amorphous material, let's say the pure amorphous drug, this is perhaps the main concern, and we need to have some idea about the amorphous stability. And that also means that we need some idea about what amorphous materials really are. Maybe we do not have always the right idea about what amorphous materials are, and I will try to spend the next few minutes on this particular question. So first of all, you should remember this, and I guess you do, is that we have a thermodynamic property here on the y-axis and temperature on the x-axis. So if we heat a crystal up, then we are increasing the temperature. We are also increasing the thermodynamic properties, such as the material's enthalpy, entropy, and so forth. And at some point, when the material melts, we have a phase transition. So the heat energy transferred to the system is now not used to change the properties of the system, but to actually change the system. And we are getting the conversion into a liquid, and that's, of course, the melt. And if we are now cooling down the melt again, we are following this path, and then the drug will crystallize again, and then it will, on further cooling, follow this path. But you already know that if we are using a sufficiently slow or hot, not slow, fast cooling rate, we can overrun the crystallization, and we are following this path now and come to the area of the supercooled liquid. So here we have a material that is out of equilibrium with the crystalline phase, so it's a high energy form, but it still is able to follow the cooling rate. So the path that we are following from the melt is still followed. But at some point in time, molecular mobility becomes so slow that the cooling rate will be too fast for the materials for any given temperature to get an equilibrium with that particular temperature. In other words, we are falling out of equilibrium with the cooling rate, and here we get a change in the slope of our thermodynamic properties, and this change in slope, not a jump, but a change in slope, is the glass transition temperature. And this is conceptually very important to remember, because it already tells us that if we are using different cooling rates, we will have different temperatures at which this will occur. So the glass transition temperature is, of course, has thermodynamic properties, but it also has kinetic properties, meaning that at a slower cooling rate, the glass transition will be lower, maybe down to here before the shift occurs, and at faster cooling rates, it will be higher. It is important that we remember that the glass transition temperature of a material is not a constant, but is depending on the way we are approaching it. You can make a thought experiment and say, what would happen if this never occurred? If I could follow this dashed line further, and eventually I would reach this point here, this temperature known as the Kautzmann temperature. And here we have a physical conundrum, because now we have a system that is still amorphous. In fact, it's still a supercooled liquid, but it would have the same entropy and enthalpy as the respective crystalline form. This is not possible, known as the Kautzmann Verbot, and therefore we know that somewhere between the Kautzmann temperature and the melting temperature, there has to be a glass transition. And what that means is that if this glass transition can be somewhat variable depending on the way we are approaching it, then that also means that we could end up at different types of amorphous materials for one and the same type of molecules. So we were looking into this, and we thought that, or maybe I go one back and just say that if we now have created an amorphous material at any temperature, we are anywhere on this line, then you can see that the amorphous material has a higher energy than the respective crystalline form. This higher energy means that it has a higher solubility, but unfortunately it also means that it has a tendency to go down this path and crystallize back. So we wanted to know if we can somehow determine the difference between the thermodynamic properties of an amorphous and a crystalline material, and maybe if this difference is large, we have a less stable system. If the difference is not so large, we have a more stable system. So we wondered if somehow the configurational thermodynamic properties, meaning the difference in thermodynamic properties of the amorphous and crystalline state, can somehow be linked to stability. So if we are going to this, what very much looks like a Gibbs-Helmholtz equation, but now is referring to the configurational free energy, enthalpy, and entropy, we can then determine the configurational enthalpy and configurational entropy on the basis of heat capacity measurements. So in other words, we can determine it by DSC, and that way we can actually determine for a given temperature the configurational entropy and enthalpy of our amorphous system. And if we can do that, we can also determine the configurational free energy. So what's the energy difference between an amorphous and a crystalline material at various temperatures? And when we do that, and we determine here, for example, in red, the configurational entropies of our various drugs, and here the configurational enthalpies, and here we have the actual stabilities, we see quite a nice correlation. It's not the best correlation in the world, but it's a correlation, right? So if we have a high configurational entropy, we also have in fact, we have a high stability, and the opposite then we follow here. And if we put this together, it gets a little less clear. If we are looking at the configurational free energy, then we see the lower the configurational free energy, the higher the stability. But there is a catch to this, these type of calculations, because we are not actually measuring the amorphous form, we are measuring the supercooled melt here. So in the supercooled melt, we are determining configurational entropy and enthalpy, and therefore we are not getting information about the amorphous form itself, because the system is a little bit more tricky. If we are in the supercooled liquid state, we are, as I told you, we are still in an equilibrium state with respect to the cooling temperature. However, if we are in the amorphous state, in the real glass, and we stop at this temperature, the system will still relax. The system will still change its thermodynamic properties, and we are maybe following this path A here. If we do that and now heat again, we are following this path, and at the glass transition temperature, we are seeing a little jump and then have the change in slope. Now, as you may know, the change in slope in the DSC in the glass transition shows as a step change, whereas a jump shows as a peak. That means that we are getting more and more buildup of a little enthalpic relaxation, we call it, above the glass transition temperature, which shows as a step change. In the DSC, this looks like this. So if we're looking here at quench-cooled simvastatin, and we have made it amorphous, and then we left it there to relax for anything between 0 and 16 hours, and we are measuring then through the glass transition again, we are seeing this buildup of this peak. And this peak is the relaxation endotherm, and that's the beautiful thing to have, because by using Kohlrausch-Williams-Watts, I spare you the details, we can determine the relaxation rate of our drug. And what we were thinking is that the relaxation rates of the drug may now somehow be connected to the stability of our amorphous material. And we did this for a lot of drugs, and we can measure the relaxation rates, and we were very happy. And then we correlated, and we saw absolutely nothing. So the stability of the different drugs is shown here, and here are the relaxation enthalpies, the relaxation rates that we can measure for these drugs. And the correlation is next to nothing. So that means that using enthalpy of relaxation or relaxation time in a Kohlrausch-Williams-Watts has no correlation to stability. And here we measured at Tg minus 20. In other words, we measured really in the glassy state. So that was very disappointing. On the other hand, it's also very clear. In hindsight, we could have expected this, because we are solely looking at one aspect of crystallization that has to do with the relaxation. But if that really is the driver for a given drug to crystallize is not so clear. But if this is so, then we can maybe still use this method if we are looking at amorphous materials that of the same material, of the same drug, but that we prepared by different pathways. So here we have indomethacin, and this is some work of Pranav, and I get a bit more modern in a minute. But here we can see that quench-cooled alpha, ball-milled alpha, cryo-milled gamma, ball-milled gamma, spray-dried and quench-cooled, they all are amorphous, but you already see that all the halos look different. And with different halos, that means we must have some differences. The halo isn't nothing. It is telling us something, and we come back to that towards the end of the lecture. But for now, suffice to say that different halos mean that something is different with the amorphous material. And we are now applying the same Kohlrausch-William-Watts enthalpic relaxation approach. We are measuring the relaxation function as a function of aging time for differently prepared amorphous forms. And we can see that they are relaxing differently. So if we plot now the experimental stability against the relaxation times, we see a beautiful correlation. So for one and the same drug, if you make it amorphous in different ways, you can very well use this approach to see whether a different alternative preparation method will lead to a more stable amorphous form or not. So that is interesting, and what it really means, the take-home message here is it matters how you make a material amorphous. It is not unimportant as it would be in the case of a thermodynamic property like the melting point, for example. So then we were looking at how can we get more information. The glass transition seems to be a wobbly candidate for determining stability. And here we work with Axel and Michael Gero, Axel Zeitler, Michael Gerin, and they, of course, we worked with them many years on terahertz stuff. And these rather unassuming curves that we see here, which is a terahertz signal just of the absorption of amorphous material, but at different temperatures. This is a very important figure here, because if we are plotting the inverse of the absorption coefficient that we are measuring, for instance, at a frequency of 1 Hertz, then we're going to see two changes in slope, one here and one here. The lower one coincides with the glass transition temperature, and the other one is coinciding with the famous beta relaxation. So that's a different form of relaxation that we can also determine that way. And what we did on top of that is we were using other methods, a whole range of other methods, but most importantly, DMA, dynamic mechanical analysis, for instance, to determine the storage modulus of our amorphous material at different temperatures. And if we do that, we're going to see, again, two changes in the slope. One at the glass transition temperature and one at the beta relaxation. So this is a very convenient way to determine the beta relaxation. It's more like an individual molecular relaxation process as opposed to the cooperative motions that cease to occur below the glass transition temperature. So when we do this, if you want to have a look at the thermograms, the DMA thermograms here, then we see nothing, 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 big peak. That's the glass transition temperature. But if we zoom in here in this area, we see that this nothing isn't nothing, but that there is a second peak, and this second peak is the beta relaxation. So again, we were then thinking, can we correlate the beta relaxation with amorphous stability? Here again, the glass transition temperature, not very useful, because we have very many drugs that have about the same glass transition temperature, but very different stabilities. And then we have drugs with very similar stabilities, but very different glass transition temperatures. So the TG alpha, we call it the glass transition temperature, does not provide adequate information on physical stability. The system looks a bit more interesting when we are looking at the change of the beta relaxation. And here, for the drugs that we investigated, we could find a correlation here. And if the the beta relaxation is actually lower than the storage temperature, we have never seen the drugs under these conditions crystallizing. So we believe that a drug stored below its beta relaxation temperature will be stable. You may remember this famous TG minus 50 rules that hangs around. maybe this is the basis for it. It's not strictly true. It is sometimes true depending on where the beta relaxation lives. And then we can fit an empirical function here to determine the stability of an amorphous material, for instance, at different temperatures. So here the proof of the pudding. Nifedipine has a glass transition temperature of 322 Kelvin and a beta relaxation of 202. So 120 degrees below TG, yeah? And only if we are above beta relaxation do we not see crystallization anymore. At other higher temperatures, after increasing times, but nevertheless, as long as we measured, it occurred, whereas the amorphous nifedipine stored at 193 remained stable, I would say, for the duration of Eric's PhD. So we believe that the beta relaxation is a very good indicator for amorphous stability. But you have also already heard that, you know, how I make the amorphous form is important. And that, of course, gives rise to a question that interests us quite a lot now. And that is the question of, can there be different amorphous forms of the same material? So could there be polyamorphism, different amorphous forms? And we call it polyamorphism if we truly have a phase transition between one and the other amorphous form. We can sometimes call it pseudo-polyamorphism if we just see that different preparation paths lead to different amorphous forms, but it's not really constituting sort of a local minimum or something like that. So here comes Ines into the play. Is a postdoc we have in our group, Ines Martins, and she is looking at hydrochlorothiazide. And I don't want to steal her thunder, but would really ask you to invite her to this forum perhaps in a few months. Then she can give you a beautiful story about the polyamorphism of hydrochlorothiazide. So what has been found earlier, in fact, by Danny Morlin and from Kiki Bergström's group, is that hydrochlorothiazide, if you prepare it by quench cooling, I believe, or by spray drying, you get very different glass transition temperatures. So very different, more different than you would expect based on different cooling rates or something like that. So now we have, like, what is this, almost 35 or so degrees different between one polymorphic form and the other. And we repeated these experiments and we found fairly similar glass transition temperatures after quench cooling, spray drying, and then yet a third one after ball milling. So the preparation method in this case leads to amorphous material, same material, but different glass transition temperatures. And so we ask ourselves, is this polyamorphism? Is this really fact or fiction? And that's what Ines is working on. And I just want to show you here the conceptual approach that we're taking here. We are making the material amorphous in different forms. We are then throwing quite a bit of techniques, and I come back to one of them in particular, at the material in order to determine similarities and differences on different levels of these two materials. And with that information, we can then go into molecular modeling, and then we can determine, for example, pair distribution functions that we can calculate from molecular dynamic simulations of the amorphous material, compare them to reality, and then we can find out if there are indeed structural differences between these different polymorphic forms. So it's a mishmash of back and forth of preparation, experimental techniques, and then modeling. And here some DSC data to just get you hooked on this fascinating topic. We have here amorphous hydrochlorothiazide prepared by ball milling. And as I have told you before, if we are changing the heating rate at which we are determining glass transition temperature, we see a shift in the glass transition temperature. The faster we heat, the higher the glass transition temperature. And we see that this is true. And this is true at the beginning and after some storage also. So this looks variable, but please note that the y-axis here goes from 150 to 118 degrees centigrade. So we have the expected behavior here for the drug prepared by ball milling, and we have also the expected behavior for the drug prepared by quench cooling. Please again note that this y-axis is very much spread out here, just a couple of degrees. But we see that an increasing heating rate leads to a higher glass transition temperature. This is what everybody would tell us. But then we got nearly a nervous breakdown when we looked at the temperature dependency of the spray dried material. And here, a higher heating rate not only has that material a different glass transition temperature, but a higher heating rate also leads to a decrease in the glass transition temperature. So I am still not sure, maybe Ines knows why that is, but I don't understand it. But it clearly shows that these different materials are not just, you know, variations of the theme, but that at least the spray dried has a very different behavior than the other two. So that's a strong indicator of a true polyamorphic form. And then, of course, we were thinking, well, this must be some differences in maybe the configuration of the molecules or the near order of the molecules. And so we determined pair distribution function. I go through this quite quickly now. So basically, what we do is we go to the synchrotron, and we are determining the total scattering of the materials. So that is not only the Bragg peaks that you normally take from an X-ray diffraction, but we collect the whole diffuse scattering, the whole reciprocal space, so to speak. And then we apply some scattering factor, and then we do a Fourier transform, and then we get curves like this. And this is showing us the probability of interatomic distances. So at very short distances, these are interatomic distances within the molecule, and then further on, maybe to the neighboring molecule. And that is, of course, beautiful if we want to look at differences in the average configuration of a molecule or in the average near neighborhood of the molecule. So if we do this, we can first also determine specific configurations that are particularly low in energy, and then we can determine out of this with molecular dynamics, we can calculate a pair distribution function. So if this was the only molecule in the world, then this single molecule would have a pair distribution function like this. And then we can look at our pair distribution functions that we got experimentally from the differently prepared amorphous forms. And what do we see? It's not 100% the same. It's not even a lot the same, but more important here is that the three forms, quench-cooled, Bornberg, and spray dried, almost had identical pair distribution functions. And this means that on the conformational level of the individual molecule or their nearest neighbor, these systems are surprisingly similar. They are not different. So the difference between these two amorphous forms must be on a larger length scale than the molecular or bimolecular length scale. That was a big surprise to us. What we, however, can say is that similarity of the single molecules PDF and then the experimental PDFs is not very good. But if we are looking at a periodic structure, so at many molecules, then we are seeing that our models are getting closer and closer to reality. And here I want to show you a little bit. Oh, maybe. Yeah, I show you this also. So then we can make the material amorphous in the molecular dynamics by different starting materials. And if we take the pure crystal, then we are reaching a very high melting point that is not realistic. But if we are starting to introduce a few defects into these crystal structures, we eventually arrive at the melting point that is also corresponding to the melting point in reality. And then we can take this material and run a longer simulation. And if we do that, we get a calculated pair distribution function. And now if we compare that to our experimental, we get a beautiful fit. This is, we were told, I'm not saying this is true, but this is probably like an unheard of fit of simulated and experimental data. So well done, Ines. So we have absolute trust and knowledge in the molecular structures that we're seeing in our molecular simulations. But the less exciting news is, or maybe even more exciting if you think about it, is that the differently made amorphous forms with very different thermal behavior and very different glass transition temperatures nevertheless seem to be identical on the configurational and nearest neighbor level. So a lot more work to do. And in fact, Ines has done a lot more work on this. And I really urge you to look at this. The take-home message for now is that your amorphous material, if you make something amorphous, it matters how you do it. And that means you need to take this into account for all amorphous work, is that you are not having the same material if you have prepared it differently, or perhaps if some impurities are present, like a second component on amorphous drugs. And here I want to show you some work we did recently to determine the effect of a small amount of material on the behavior of amorphous materials. And this is some work that Jing Wen has done. She has just finished her PhD, she's just submitted. If you want, I give you the date for her defense, and you should all join, and then she'll be super happy. But we make a material amorphous. Then we have for example, we call it co-amorphous here, but it's only 1 to 3% of more or less like an impurity, if you like. And then we are converting that into an amorphous disk with the use of a melt prep thing. We heat that up a little, we put a cover glass on top, we get a very thin film, and onto this film we are pressing a grating with a certain frequency, so nanometer type grating on it. And this sinusoidal surface, then we are watching how it decays over time with an atomic force microscope. So that's the way we are doing this. And this is the type of data we get. So we have the amorphous sample, we put the grating on, and then we are looking at the height of these gratings going down. And this is following some physical function. And if we do everything right, then this decay will be only determined by the surface mobility of the material. So in the AFM, you can see here the sinusoidal graded surface. You can see here that with the imprinted grating that we're using here, it's about 100 nanometer, the amplitude of this, and it's fairly reproducible here, the height, and we have a very narrow height distribution in average here of 100 nanometer. And then over time, this flattens out, and we can measure this flattening out. And if we do this as a function of different gratings, and we get a beautiful slope around 4, then we know from so-called Mullen's model that we are really measuring surface mobility here, or we can say surface diffusion leading to decay of the height of these gratings. And so for that, we need a very thin film here. You can see the film is very thin, but it's still much, much thicker than is the ondulation or the grating on it. And if we are now adding, for example, small amounts of aspartic acid to amorphous carvadilol, we see hardly a difference in the halo. We see very little difference in the glass transition temperature because we are adding only a small amount of the other material. And we do see, however, an ever increasing difference between the theoretical and the measured glass transition temperature. This is because the aspartic acid will form a salt with the carvadilol, but at these few percentages, this is mole percent, we are only getting a slight deviation. But then if we are measuring the decay for these different materials, we get curves like this. And then if we plot those curves, or the logarithm of the decay constant here as the dots versus the actual physical stability, then we can see that already small amounts of an impurity can increase the stability of the material quite dramatically. And this, in our view, opens up new possibilities of stabilizing pure materials, not by converting them into an amorphous solid dispersion or a full-blown co-amorphous system, but by doping it, so to speak. We've done similar measurements, not with small molecules, but also with polymers, and have seen that already small amounts of polymer can go, or other material can go a long way to stabilize the system. And that's what we learn here. And in the end, I want to show you another effect of a small addition of a material on an amorphous material. And here, Xi Zhou is looking at this. She has more or less just started her PhD, but has done some very beautiful work on the influence of water on these materials. So what we know from the literature is that prilocaine is a strange material because water is not a plasticizer for it, but an anti-plasticizer. And we were wondering, is this the same for lidocaine, which has a similar amide sort of structure here that is believed to be the reason for the anti-plasticizing effect of water on this particular drug. So the idea is that water is binding to 2 of the prilocaines, so we have a unit that now has a lower, is bigger, and therefore has a slower mobility, maybe a higher glass transition temperature. And we thought, like, is this the same for lidocaine? And I thought this was a very simple piece of work until we found out that you cannot make lidocaine amorphous. It is just so fast crystallizing that we could never make the material amorphous. So we had to go a beautiful detour here. We are making initially co-amorphous systems of prilocaine and lidocaine. We are then measuring if water has an anti-plasticizing effect on that, and then we can extrapolate that back in one way we are doing these experiments to the effect of water on pure lidocaine. And I just show you these kind of data we're getting here, is that if we are adding water, this is the mole fraction of water, to our amorphous or co-amorphous system, we see for prilocaine that the addition of water leads to an increase in the glass transition temperature until we get full hydration of the material at about 50 mole% of water, and then it stays the same. But if we are having increasing concentrations of lidocaine in co-amorphous systems, we see that we still get this slope, but this increase in glass transition temperature as a function of water concentration, but the slope is getting lower and lower. But if we are plotting the slopes here, in fact, we're plotting the reverse of the slope against the concentration, we still see that we have a positive slope if we have extrapolated to pure lidocaine. So with this and other measurements, then Chirurgie could show that the amorphous, that lidocaine, even though we cannot make it amorphous, if we could make it amorphous, then water would also be an anti-plasticizer for lidocaine. And now we are looking at other aspects of this peculiar phenomenon, for instance, lidocaine together with other materials and so forth. So this is just to show you that small amounts of material can have an effect on the amorphous material. So your amorphous drug is depending on the way you make it. It's depending on how old it is. It's depending on how much other stuff is there. And all of this we need to know to have a good basis for amorphous drug development. So I hope in the last 50 minutes I could convince you that looking at drugs only, if you doing amorphous work is a very worthwhile thing to do. We have to look at the amorphization path, the propensity of the drug to amorphize, supersaturation propensity, amorphous stability, possible pseudo or full-blown polyamorphism, and then also the effect of other components on that drug. And then I think we are in a very good position to start understanding also the more complex formulations such as co-amorphous systems and amorphous solid dispersions that we are of course also working on, as do many others, and we do this of course also in collaboration with many others. So for now I'd like to thank you for your attention, and at this point I stop sharing and I'm happy to answer questions.